Last time we sketched a proof of Nash's theorem, which argues that every game must have an equilibrium. But unfortunately, that proof was non-constructive, so it doesn't actually help us find a Nash equilibrium. The problem, from a computational point of view, is that when we cited Brouwer's theorem, it told us there must be a fixed point, but said nothing about how to locate it. So in this video, I want to dig into Sperners' lemma, which is one way of proving Brouwer's theorem, because the proof shows us a way of narrowing in on a fixed point, and maybe we can use that to help us find a Nash equilibrium. But I don't want to just state Sperners' lemma and spend an entire video proving it and Brouwer's theorem. You can and should read the proofs in the multi-agent systems textbook, which take that approach. But at least for me, that level of abstraction doesn't provide great intuition. And so instead, I want to think about a slightly different case, where Sperners' lemma leads more directly to a sketch of an algorithm. And that is the problem of finding symmetric Nash equilibria in symmetric games. A symmetric game is one where all of the players have the same incentives. So it doesn't matter if you are taking on the role of player 1 or player 2 or any other player number. Or another way to say it is that the payoff matrix looks the same under any permutation of the players. Many of the games we've seen are symmetric. Chicken, rock, paper, scissors, and Prisoner's Dilemma are all examples where it doesn't matter if you are player 1 or player 2. But the idea of symmetry extends to any number of players. If I have a game with 100 players, it could still be symmetric if it doesn't matter which player is which. And what we'll be proving is a special case of Nash's theorem, that in a symmetric game, there must be a symmetric equilibrium where all of the players are following the same mixed strategy. The players still randomize independently, so they can end up with different actions, but in a symmetric profile, every player is using the same mixed strategy probabilities to do their randomization. And the reason this helps is that if everyone is playing the same mixed strategy, we only need to represent it once, rather than tracking a separate mixed strategy for every player. To make this more concrete, let's think about chicken, and specifically about the vector representation of the 3 Nash equilibrium profiles. In chicken, we have 2 pure strategy Nash equilibria, stop-go and go-stop, and represented as mixed strategy profile vectors, those correspond to the probabilities 0, 1, 1, 0 for stop-go, or 1, 0, 0, 1 for go-stop. But neither of these profiles is symmetric because the 2 players are using different strategies. On the other hand, the mixed strategy Nash equilibrium, where both players randomize 1% go, 99% stop, is a symmetric profile. Since both players use the same mixed strategy, it's redundant to write that mixed strategy twice, so we can simplify our representation by writing the symmetric profile using just one probability per action. But we can also think about other profiles that aren't necessarily Nash equilibria, such as these mixed strategy profiles for rock, paper, scissors. Since rock, paper, scissors has 2 players who each have 3 actions, a mixed strategy profile needs to specify 6 probabilities. The first 3 give us the mixed strategy for player 1, and the next 3 give us the mixed strategy for player 2. And in this first profile, we see that the players are using different mixed strategies, and so this is not a symmetric profile. Whereas in this second example, both players are using the mixed strategy 0.2 rock, 0.1 paper, 0.7 scissors. And so again, we can represent this more compactly by just giving the probability for each action that all of the players are using. And so this representation of a symmetric profile means that we no longer need to specify a probability for every action of every player. And so the dimension of the vector no longer depends on the number of players. If the symmetric game has 3 actions for each player, then a symmetric profile can be represented with a vector of 3 probabilities that lives in the standard 2-simplex. Before, when we had a dimension of the vector for every action of every player, if we had a game with 50 players who each had 10 actions, then a profile would need 500 dimensions to specify all of their strategies. And that vector would live in a 500-dimensional symplectope. But if the game is symmetric, then we can represent a symmetric profile by just specifying a probability for each of the 10 actions. And so now our vector lives in a 10-dimensional simplex. But now that we've redefined our representation of a symmetric profile in a symmetric game, we have to modify all of our definitions from Nash's theorem to apply on these symmetric profiles. When we talk about a deviation payoff, which is the expected utility of deviating to one specific action while everybody else plays according to a profile, that deviation payoff is now the same for any player. Since in a symmetric game, everyone has identical incentives, if I deviate away from the mixed profile to play action A, I would get the same payoff as if instead you deviated away to play action A. And so we'll have a deviation payoff for each of the actions, and that's an expected utility, which has to sum over all of the outcomes in the game. Of note, our representation of the profile now makes no reference to the number of players. If we have a game like Rock, Paper, Scissors that has 2 players and 3 actions, we get a 3-dimensional symmetric profile. And we also get a 3-dimensional symmetric profile if we have a 100-player game with 3 actions. Where the number of players makes a difference is that the number of outcomes is exponentially larger as we get more players. And so computing these expected utilities that sum over all of the outcomes in the game very much depends on the number of players. Just like with the deviation payoff, our mixture expectations no longer need to specify which player we're talking about, since everyone is playing the same mixed strategy, and everyone has the same incentives. The expected utility of the mixed strategy is the same whether I'm player 1 or player 2 or any other. And now our Nash advantage function, which operates on the profile representation, no longer needs to handle every action of every player. Instead, it's just defined on each action. So it takes as input a symmetric profile whose dimension is the number of actions, and it outputs another symmetric profile. And under this definition of the advantage function, if we have a fixed point where the probabilities don't change, that must mean that the gain for every action was 0, which in turn means that the symmetric profile must be a Nash equilibrium. And this advantage function, just like the one from last time, meets all the conditions of Brouwer's fixed point theorem. And so Brouwer's theorem would tell us that a fixed point exists, and there must be a symmetric Nash equilibrium. But since our goal was not just to say an equilibrium exists, but to actually find it, that's not good enough, and we need to dig deeper. If we want to actually go looking for a fixed point of this function and find a symmetric Nash equilibrium, then we again need to think about the space in which we are searching. And since our symmetric profiles have everyone playing the same action, we just have a probability distribution over the actions, And so our symmetric profile vector lives in a simplex. For the 2 and 3 action simplices, we can draw them and think about different symmetric mixed strategies as different points in our drawing. And this will help a lot with providing intuition. But of course, many of the games we would want to solve will have more than 3 actions, and so we'll have higher dimensional simplices. Since our goal is to find a point in the simplex that is an approximate Nash equilibrium of the game, we will need to have a way of determining how to narrow in on the right points. And the first step of this narrowing in is to subdivide the simplex. What we're using here is an edgewise simplicial subdivision, and I'll post a link to a video that goes into more depth on that. But the key point is that we can divide up the simplex and then pick a subsimplex and recursively subdivide it. And for any subsimplex that we decide to zoom in on, we can think of all of the points in that subsimplex as some mixture between the vertices that define the subsimplex. Just like any point in the full simplex can be expressed as a convex combination of the vertices, any point in this subsimplex can also be expressed as a convex combination of the subsimplex vertices. And that's true no matter the dimension of our simplex. And so, when we zoom in to some subsimplex, we will redefine our coordinates to be specific to that subsimplex. Since every point in here is defined by a unique convex combination of the vertices, we will call the simplex coordinates for the point the multipliers on that convex combination. So just like up here, the middle point of the simplex would be 1/3, 1/3, 1/3, and a point on the boundary of the simplex would have a 0 in one of its coordinates, and so on. So our goal here, to zoom in on a Nash equilibrium, will be to subdivide the simplex, identify the right subsimplex to zoom in on, change our coordinates to be in terms of that subsimplex, and then continue recursively by subdividing our new smaller simplex. And so now our goal is to make sure that the subsimplex that we're zooming in on is one that contains a fixed point of the advantage function and therefore a Nash equilibrium. And we ensure that by zooming in to a subsimplex that is completely labeled according to the Brouwer labels. So when we subdivide the simplex, we get a bunch of vertices of the subsimplices. And each of those vertices will get a label according to the advantage function. And the way we'll label a vertex is based on which of its dimensions the advantage function decreases the most. So we'll say, for this point, if we applied the advantage function to that point, where would it go? And then, among the dimensions that we use to represent this point, and when we look at the vector we use to represent this point, which dimension of the vector decreased the most when we applied the advantage function. But we are first of all restricting that label to only be one of the dimensions that is non-zero at that point. So this point could not have the label for this dimension. Its label will only be one of the non-zero dimensions. And that is, of course, in terms of the simplex coordinates for the subsimplex that we're currently operating on. So, if we have subdivided the simplex and given a label to every one of the vertices, our goal is to find some subsimplex where all of the vertices have different labels. And the reason we want a completely labeled subsimplex is that if we have a really small subsimplex where the label is different for all of its vertices, then there must be a point in that subsimplex where we switch between all of those different directions that the advantage function is pushing, and that will be our fixed point. So this gives us an idea for an algorithm we could use to try and zoom in on a Nash equilibrium. We'll start by subdividing the current simplex, and we will label all of the vertices of the subdivision in the simplex coordinates of whatever subsimplex we're currently working on. Then we will identify a completely labeled subsimplex and zoom in on that subsimplex and recurse. And we'll keep recursing smaller and smaller until we get to some small enough size of subsimplex where we know that we have an epsilon equilibrium. And I claim that the limit, as we zoom in on smaller and smaller subsimplices, must be a fixed point of the advantage function. Which would mean that if we were to recurse infinitely small, we would find an exact Nash equilibrium. And if we stop the recursion after some finite number of steps, we'll have an approximate equilibrium. So to prove this claim, we would need to show that we can always find a completely labeled subsimplex. And that's where Sperners' lemma comes in, so we'll come back to that. But if we can always find a completely labeled subsimplex to zoom in on, then we need to argue that this process approaches some limit, and that limit is a fixed point of the advantage function. So the reason why there is in fact a limit point is that we are always zooming in, so we are contained in a smaller and smaller subregion, and since the simplex is compact, we know that the limit of any such sequence must also be in the set, and so there is in fact such a point. And the reason we know that limit is a fixed point of the function is because the advantage function is continuous. Because of continuity, there can't be any big jumps in the function, and so as this simplex closes in on its limit point, if it's always true that the vertices have different labels, then we know that close around this limit point, the advantage function is causing the greatest decreases in different dimensions. And as long as the greatest decrease that we've used to set these labels is never actually an increase, the only way that we could have the function be weakly decreasing in all of these different directions, arbitrarily close to our limit point, is if we are approaching a point where the change in all of the dimensions is 0 at that point. So I said we need to be sure that the label we gave is always a dimension that's not increasing. And we know that's the case because when we set the label to the thing that decreases the most, there's no way for the advantage function, which takes in a profile and outputs a profile, to increase the probability on every dimension. Since the output will still be in the simplex, the output still has to sum to 1, and so you can't take a profile where the probabilities all sum to 1, increase all of the probabilities, and have it still sum to 1. So there must always be at least one dimension that advantage is causing to weakly decrease. And so, because the advantage function is continuous, the limit of this zooming in must give us a point where all of the dimensions are unchanged. And that is, by definition, a fixed point of the function. So now we need to come back to Sperners' lemma and think about why we can always find a completely labeled subsimplex. And the way we know there is such a subsimplex is that Sperners' lemma tells us the number of completely labeled subsimplices is odd. And we can prove that by induction on the dimension of the simplex. So if we start as a base case with the two-action simplex, we know that when we labeled this two-action simplex, our labels were only allowed to be things that had non-zero probability at that point. And so each endpoint of this segment has to have a different label. This one will be labeled with dimension 1, and this one will be labeled with dimension 2. And so if we think about a subdivision of this simplex into a bunch of smaller simplices, and we label all of the vertices of the subdivision, since this label is 1 and this label is 2, there must be somewhere along the segment where we go from a label of 1 to a label of 2 on consecutive vertices. And the simplex between those consecutive vertices is completely labeled. So we have at least one. But we might have more. It might be that there are consecutive vertices with different labels, and then later that happens again. But the next time it happens, we would have to have a label 2 followed by a label 1. And if we now have a label of 1, then by the time we get to the end, there must be a case where we have a 1 label next to a 2 label. And so after the first completely labeled subsimplex, if we have another, it must come with a pair. And so when our simplex is a line segment, there must be an odd number of completely labeled subsimplices. Now for the inductive case, we assume that any simplex on n dimensions must have an odd number of completely labeled subsimplices. And we want to argue that this means any simplex on n+1 dimensions must also have an odd number of completely labeled subsimplices. Here I've illustrated this going from a 2-dimensional simplex to a 3-dimensional simplex, but our inductive argument needs to be fully general going from n to n+1 dimensions. So if we have an n+1 dimensional simplex, the boundaries of that simplex must be n-dimensional simplices. Here our simplex in 3 dimensions has edges that are simplices in 2 dimensions. And so if our outer simplex has different labels at each of the vertices, which it must, again, by the way we have chosen the labels to only pick things that have non-zero probability, then when we subdivide the simplex, if we look at one of its faces, the subdivision of the n+1 dimensional simplex also subdivides the n-dimensional face. And so by the inductive hypothesis, we know that on this face there must be an odd number of completely labeled subsimplices. And completely labeled on this face means it uses all of the possible labels of the larger simplex except for 1. And then if we look at one of those completely labeled n-dimensional simplices on the face, and which n+1 dimensional subsimplex it's a part of, then we know that this subsimplex, the triangle in my drawing, must use at least n labels, since the face was completely labeled. And it's possible that this label will be a new one or a duplicate. If it's a new one, then we have found a completely labeled subsimplex. But if it's a duplicate, then we can define a walk through the simplex to try and identify something that's completely labeled. So here we have a walk that is entering the simplex along a completely labeled face. We have the labels 1 and 2 on this edge, but the additional label of the n+1 dimensional subsimplex is a duplicate. So this subsimplex is not completely labeled, but we know that there's only one duplicate label, and so we can cross over the face where we take out the previous instance of the duplicate label and add in the new instance. And if we cross over that face, then we go into another subsimplex, which we know must have, at worst, all but one possible label. Because the only duplicate was these two, and we removed one of the possibilities that was a duplicate, now we know that this face was completely labeled in n dimensions, and so the simplex is almost completely labeled in n+1 dimensions. If it is completely labeled, we've found the end of our walk, but if not, then there is at most one duplicate, and again, we can swap in the new instance of the duplicate label for the old one and cross over that face into a new subsimplex. And this walk will keep going until it either arrives at a completely labeled subsimplex or until it leaves the simplex entirely. But because the duplicate label must have been one of the labels from this face, if we ever hit the missing label, we're done. So the only way that we could keep going is if we keep having duplicate labels that are one of the labels on this face. So the only way this walk could leave the simplex is by crossing one of the other completely labeled simplices from this face. And so, because there were an odd number of completely labeled n simplices on this face, and the walks will either arrive at something completely labeled or pair up two of these, there must be at least one walk that arrives at a completely labeled subsimplex. So because we had an odd number of completely labeled n simplices on the face, we must have at least one completely labeled n+1 simplex in the overall subdivision. But that doesn't yet guarantee that the total number in the subdivision must be odd. But we know that this walk always crossed over a face that had all of the labels from this edge. So if we start from a completely labeled subsimplex and do the same sort of walk where we always cross over the face that has these labels, well, from this subsimplex, that would just take us backwards along the same walk. And so whenever there's a walk in one direction, there must also be a walk in reverse. And we could do such a walk starting from any completely labeled subsimplex. So if you find some other random completely labeled subsimplex and start following this walk, you will either arrive at another completely labeled subsimplex, or you will leave the whole simplex, but the only way to leave the whole simplex is out this edge. And so there could be other completely labeled subsimplices that we can't arrive at by walks from this edge, but they must come in pairs. And so, because we find an odd number by walking from this face, and there are an even number of others that we can't find that way, the overall number of completely labeled subsimplices must be odd. So what we've argued here is that if we have an odd number of completely labeled subsimplices in n dimensions, we must also have an odd number of completely labeled subsimplices in n+1 dimensions. And so inductively, the number of completely labeled subsimplices is odd for any dimension of simplex. And so, because 0 is not an odd number, there must be, no matter what number of actions in our game, at least one completely labeled subsimplex. And when we label this subsimplex, we will get different labels on all of its vertices. And then when we subdivide and relabel the subsimplex, the same property will hold. So there is always some completely labeled subsimplex that we can zoom in on. But unfortunately, that doesn't mean that we can find it. Take a moment while I update the whiteboard to pause the video and see if you can find the hole in the reasoning here. Our inductive argument does prove that the number of completely labeled subsimplices must be odd. which means that a completely labeled subsimplex must exist, which is all we need for parts 2 and 3 of this proof sketch. So it will be possible to zoom into a limit, and that limit will be a fixed point of the function. But the trouble is, we only know how to find one of the completely labeled subsimplices in n+1 dimensions. Our argument was that if we have an odd number of completely labeled n simplices on the face, then at least one of them must lead us on a walk that finds a completely labeled n+1 simplex. And our argument said that if there are other completely labeled subsimplices, there must be an even number of them. But it didn't tell us anything about how to find these other ones. And when we go one more dimension up, if we want to even be able to find one completely labeled subsimplex, we have to have all of the completely labeled subsimplices on one of the faces. If we only have this one, then it might be that one dimension up, this leads us to one of the walks that comes back out the edge. And to find a completely labeled subsimplex in the next dimension, we might need to start from one of these, possibly many other, completely labeled subsimplices. So before we could go up another dimension, we would need some way of tracking down all of these other completely labeled subsimplices, and we don't have a procedure for doing that. In principle, we could exhaustively explore every subsimplex, but that gets out of control really fast in higher dimensions. So, if all of this doesn't give us a practical algorithm, what was the point? Well, for one thing, we did prove that a symmetric game must have a symmetric Nash equilibrium. And I hope that this exploration has given you better intuition for Sperners' lemma and Brouwer's theorem. In particular because there was nothing special about our use of the advantage function in this proof. We could have gotten our Brouwer labels from any other continuous function on the simplex, and so replacing advantage with an arbitrary continuous function makes this into a proof of Brouwer's theorem on the simplex. And that actually gives a basis for proving Brouwer's theorem in general, which you can do by transforming other convex sets into the simplex. But since this approach didn't give us an effective algorithm, we'll have to explore other approaches for computing a Nash equilibrium soon.